basic exponential function is y equals f of x equals 2 to the x. So, if you have x values, -2, -1, -1/2, 0, 1/2, 1, 2, some of these are crossed out and we'll see why. Then you can substitute these x values into the f of x equals 2 to the x and obtain the y value. So, we have x equals -2, we plug in -2, we find that f of -2, x has been replaced by -2, is equal to 2 raised to the x, which is 2 raised to the -2, since x is now -2, at least for the moment. And 2 to the -2 is 1 over 2 squared, which is 1/4. If x is -1, well, the same process tells us that y is 1/2. f of -1 will be 2 to the -1, 1 over 2 to the 1, which is 1/2. f of -1/2, turns out you don't know how to calculate that. You have to use a calculator. We're not going to use a calculator. And we're not going to use a calculator because we really need to understand these numbers, where they come from and why they are what they are, so we understand the function a little better. Okay, so we get f of -1/2 is 2 to the -1/2. Again, x has been replaced by -1/2, so x is replaced by -1/2 here too. That gives us 1 over 2 to the 1/2, but now we're stuck because we don't know how to calculate 2 to the 1/2. Okay? No, I know how to calculate 2 to the 1/2. I know how to calculate it to a million decimal places, although I don't have time to do that, and I'd probably never manage it without making a mistake, even if I did have time. We could program a computer, a supercomputer, to give us trillions of decimals of 2 to the 1/2, but none of them are going to be completely accurate. I mean, they're going to get pretty close, really, really close, but they're never going to be accurate. They're never going to be exact. Okay, accurate. Yeah, they're going to be more and more accurate, but they are never going to be exact. And one of our rules for the basic function is going to be we don't use a number that gives us a calculation that can't be expressed exactly. Okay, so we don't use it. We don't use -1/2. We eliminate -1/2 from the domain of this function. Okay, now, if x equals 0, then f of 0 is 2 to the 0. And people often want to write 0. It messes up the graph, messes up the whole shape of everything, misleads you, and ignores the fact that 2 to the 0 has been defined to be 1. The reason for that, you can look at my notes for the MDE 60 class. The pre-calculus of the intermediate algebra class, I explain why that is. At least I give some good reasons. There's a little circularity in the explanation, but nobody's really going to understand that. Okay, so anyhow, f of 0 is 2 to the 0, and any number to the 0 power has to be 1. Okay, if x equals 1/2, again, you got to do 2 to the 1/2, and you're going to exclude that value. So I do this little green mark through here, indicating that we don't get y values for these, so we don't include these x values in the domain. There are y values, we just can't ever express them in decimal form or fractional form with complete accuracy. Okay. If x is 1, then f of 1 is 2 to the 1. If x is 2, we get f of 2, which is 2 to the second. Well, 2 to the 1 is just 2. 2 to the second is 4. And now we've got 5 points. Okay, well, these 5 points, and unfortunately we had technical glitches. Was not able to record this live, but the 5 points are the points in blue here. And those 5 points, without the curve, without anything else, constitute our basic exponential function. The domain of that function is the set of x values, and the range is the set of y values. And well, the y values are 1/4, 1/2, 1, 2, and 4. Right there they are. There's the domain, there's the range. Okay? We could represent the domain with little x's down here on the x-axis if we wanted to. and the range by the values, this one, this one, this one, this one, and this one. We don't have this value in the basic exponential function. Now, we do what I call the extended basic function. Don't use that name in polite society because it's not a standard name, but I want to distinguish the domains and ranges of these, so I use some terminology. Basic function is a discrete function with 5 numbers in the domain and 5 numbers in the range. The extended basic exponential function is the function represented by the smooth curve through these points. That's in orange, that's the color. And now the domain of this function is the set -2, 2. I'm sorry, the interval -2, 2, the closed interval -2, 2, meaning the interval that starts at -2, including -2, ends at 2, including 2, and all the numbers in between. So right here on the x-axis we see a representation of the domain of the extended basic function. The range of the extended basic function is the set of all the y values. Well, the y values for this curve and this extended basic function is just on the domain -2, 2, so it starts here and ends here. Now there's the complete exponential function, which goes from -infinity to infinity and so forth. We'll talk about that in a second. But the extended basic exponential function is on this domain, so the smallest y value in this domain is 1/4. And the largest is 4, and it's a nice smooth curve, there are no breaks. So the range is the interval, closed interval, 1/4, 4. The set of all y values starting at 1/4, ending at 4, and all numbers in between. Now one thing I'll say here, well, first let me talk about the complete basic exponential function, which of course just goes on forever, this way and this way. That's because no matter what number you want to choose for x, you get a y value. We can raise 2 to any power whatsoever. So if x is a negative number, well, we see that if x is 0, we get 1. If x is -1, 1 unit in the negative direction, we get a half. At -2, it's a fourth. If x was -3, it would be 1/8, half of a fourth. Every time we move 1 unit to the left, the value of the function becomes half as great. Well, this continues forever, and we never get 0. There's no number other than 0 whose half is equal to 0. So the numbers get really small. We could cut things in half, they get really small pretty quickly. But they never get so small that they give you 0. They get really close, close as you like. There's no limit to how close. Going in the positive direction, we can raise 2 to the 7 million power. Okay, that would be an unfathomably huge number, but it exists. At least we say it exists. Okay, it's consistent with everything else about mathematics, so in the mathematical realm we say that this number exists. So this graph gets really steep, really fast. These numbers just take off, but there's no end to it. So the domain of the complete basic function, which is defined from -infinity to infinity, is the interval, open interval, -infinity, infinity. Okay, you'll see some of this in your homework, so I'm not going to write it out here. I think we've got the idea. And the range is everything from 0 on to infinity, but not including 0, so it's an open interval. And it's open at both ends. It's open at 0, meaning it doesn't include 0. It's open at infinity, because infinity isn't even a number. It's just something we approach. We never actually get to it. Okay, that's that. Now, let's talk about this number, let's say 2 to the -1/2. That number exists. I can't give you the complete proof. I mean, I could, but You need much more advanced mathematics than you get in the first 2 years of a curriculum. Even a mathematics major or engineering major will probably not see that until at least the junior level course. The idea, though, is that we can draw this smooth curve. So if this smooth curve really does represent the function approximately, but if it's representative, then every y value between 1/4 and 4 will be taken, and there's certainly going to be a y value when x is 1/2, because this point here has a y value that's equal to 2 to the negative 1/2. To get that y value, we just do a projection. We just go straight up to the graph and straight over to the y-axis, and right there is the position of that value as sketched on this approximate sketch. So we try to estimate that value. Now here's a better picture of it. Okay, here's -1, -1/2, and up here's 1. Here's your curve. Come up to the curve and across here, and there's f of -1/2. Y is equal to f of -1/2 at this point. And then we tried to estimate that. We estimated it from this picture. We estimated it from this larger picture. Estimates were, well, we can narrow down. What's the value? Well, it's more than 1/2 very clearly, because this point is clearly above the 1/2 point, which would be correspond to x equals -1. Yeah, come out of there, okay. So, there we have 2 to the -1, which is 1/2, as we've seen. And 2 to the 0 is 1. So 2 to the -1/2 is clearly between 1/2 and 1. And by the picture, it's obvious it's between 1/2 and 1. By the picture, you could estimate the value of this. Now, it's less than halfway between 1/2 and 1. So you're going to estimate it just at one decimal place. It's either going to be 0.6, 0.7, 0.8, or 0.9. To determine whether you think it's 0.6 or 0.7, because okay, well, this point is clearly closer to 1/2 than it is to 1. 0.8 and 0.9 are closer to 1 than they are to 1/2. So if we're limiting ourselves to rounded tenths, this is either 0.6 or 0.7. Now if I divide the interval from 1/2 to 1 in half and ask, okay, is this point closer to here or here? Well, it looks to me like it's closer to here than it is to here. 0.7 would be closer to the halfway mark, which is 0.75, than 0.6, and 0.6 would be closer to 1/2. So from where this point is, we estimate that the value of 2 to the -1/2 would be about 0.7. And it turns out that's quite close. If you draw this curve carefully, you'll almost inescapably come up with the estimate of 0.7. Now, 0.7 what? Is it 0.71, 0.72, or is it maybe 0.68, which of course rhymes to 0.7? Turns out it's like 0.707, and it keeps going. It's a reciprocal of 1.414 up to a certain extent, but then that number keeps going. So there we have it. So these are a few things we can get, starting with the idea of the basic exponential function. And since your homework is going to be on functions, and then the next homework is going to be on domain and range, this should be a useful picture to you.